In May 1940 in Washington, D.C., the President of the United States set a number that sounded unreal. The nation should build 50,000 military airplanes each year. Across the Atlantic in Berlin, senior officials of the Luftwaffe dismissed the pledge as fantasy. They believed the United States made refrigerators and cars, not fighters and bombers. The mockery mattered because airpower was already deciding campaigns. Poland had fallen. France was collapsing. The Royal Air Force stood alone over the Channel. The question for this film is direct. How did the United States move from a peacetime baseline to aircraft output that would overwhelm the Axis, and why did that shift prove decisive? The setting in mid-1940 was not favorable. The Army Air Corps remained small. Factories in Detroit, Los Angeles, Seattle, and Buffalo were tuned for consumer production. Skilled labor for precision airframes was limited. Aluminum and machine tools were finite. Engine test cells were scarce. Training pipelines for mechanics and inspectors were thin. Yet the geography of the United States offered depth. Rail lines linked ore fields to smelters and smelters to plants. Ports linked plants to oceans. A continental market already knew how to move parts at scale. Those facts formed the raw material of strategy. Leadership framed the stakes in plain terms. If the United States could not build fast enough, it would fight short of airplanes in every theater. If it could build fast enough, it would choose the time and place to apply pressure. Industrial policy became war planning. Schedules would determine operations. The War Production Board would soon allocate metals. New plants would rise beside rail spurs. Automobile lines would convert to wings and fuselages. None of that was inevitable. All of it required dates, quotas, and enforcement. By late 1941, the ramp was visible. Acceptance totals began to climb month by month. In 1942 and 1943, the curve steepened. By 1944, the United States would peak near 100,000 airplanes in a single year. That peak changed the balance of power in Western Europe, the Mediterranean, and the Pacific. This episode follows that arc from pledge to production to air superiority. It asks what levers mattered most and shows how numbers on factory ledgers became combat strength in the field. The road to mass aircraft production began before formal entry into war and moved in measured steps tied to dates and places. In 1939, planners inside the United States Army Air Corps drafted expansion programs that defined how many combat groups would be needed if conflict widened. The fall of France in June 1940 and the sustained air battle over southern England later that summer transformed those studies into policy. In May 1940, the president set a public goal of 50,000 airplanes per year. That number forced a question onto every factory floor and into every budget hearing. Could the United States convert consumer capacity into airframes, engines, propellers, and instruments on a wartime clock? The first levers were administrative. In May 1940, the National Defense Advisory Commission began to link industry leaders with procurement officers to map bottlenecks in aluminum, rubber, steel, and precision machine tools. In September 1940, the Selective Training and Service Act created a legal pathway to expand the labor pool for both the armed forces and defense plants. That same month, the Destroyers for Bases Agreement signaled a political commitment to aid Britain and to prepare Atlantic infrastructure. In October 1940, the Tizard mission brought cavity magnetron radar and other technologies to North American laboratories, setting up the electronics supply chain that modern aircraft would require. Each step added a necessary piece, but none solved the central scale problem. Finance and plant building followed. In 1940 and 1941, the Reconstruction Finance Corporation used the Defense Plant Corporation to fund government-owned contractor-operated factories. The model placed public money into new buildings, presses, furnaces, and test cells while private firms managed output under contract. Ford broke ground at Willow Run near Detroit for a moving line that would assemble heavy bombers. North American Aviation expanded at Inglewood in Southern California to build single-engine fighters. Douglas and Lockheed grew in Southern California to produce medium bombers and transports. Boeing prepared new space in Seattle and Wichita for heavy bombers. Rail sidings were laid. Overhead cranes were installed. Tooling orders were placed months ahead to ensure jigs and fixtures arrived before the first wing spar reached the line. Procurement rules evolved as strategy clarified. In January 1941, the Office of Production Management began to assign priorities so that scarce alloys and bearings reached the plants that could turn them into finished airplanes fastest. In March 1941, the Lend-Lease Act authorized transfer of aircraft and engines to allies whose survival affected the security of the United States. That law converted moral support into scheduled deliveries. It also forced American managers to build capacity beyond the needs of any single service. Contracts now specified monthly acceptance targets by model and by theater. That language turned the pledge of 50,000 into dated tables. Manpower and training scaled in parallel. Technical schools in places such as San Diego, Los Angeles, Wichita, Fort Worth, and Buffalo trained riveters, machinists, welders, inspectors, and engine mechanics. Women entered tool rooms and assembly bays in growing numbers as men left for uniformed service. Unions negotiated shift rules for 2-shift and 3-shift operations. Safety engineers wrote standard procedures so that new workers could produce to tolerance on complex assemblies with minimal rework. The goal was not only speed. The goal was repeatability measured in acceptable units per day. Materials policy tightened next. Bauxite mining expanded to feed smelters that produced aluminum ingots. Rolling mills scheduled plate for wing skins and extrusions for stringers. Foundries increased output of magnesium and light alloys for castings. Rubber priorities protected tires and fuel lines. Steel allocation committees balanced demands from ships' tanks and artillery against the needs of aircraft plants for high-grade sheet and tubing. Every allocation decision moved a number on a monthly acceptance chart. By mid-1941, the United States Army Air Forces replaced the United States Army Air Corps as the service reorganized for war. The Air War Plans Division integrated operations goals with production schedules so that sortie rates in named theaters had matching acceptance curves for fighters, bombers, transports, and trainers. When Japan attacked in December 1941, the framework was in place. Within weeks, the War Production Board would formalize priority ratings and halt civilian automobile production so that machine tools, labor, and floor space could shift toward airframes and engines. The causes and the buildup were therefore cumulative. Strategy set the goal. Law unlocked finance. New plants and training made the goal physically possible. Priority control and materials policy made it reliable over time. The opening moves of the production campaign unfolded as a dated sequence tied to specific floors and flight lines. In June 1941, at Seattle Plant 2, Boeing's jig bays began to pulse with a steadier rhythm as wing and fuselage sections for the B-17 moved from fixture to fixture under gantry cranes. Acceptance officers from the United States Army Air Forces set up desks beside the line with logbooks and gauges. Across-town planners in Wichita finalized drawings for new bays that would later handle sections of the very heavy B-29, but in this first phase they concentrated on tooling, crew training, and supplier timing, so that no station sat idle for lack of a casting or a spar. The rule for the season was straightforward. Every hour not producing had to be explained. In Southern California, the pattern looked different, but served the same goal. At Inglewood, North American Aviation ran mixed lines for the P-51 and for advanced trainers that would fill pilot schools. At Long Beach and Santa Monica, Douglas ran parallel efforts for medium bombers and transport airframes, with parts arriving by truck from subcontractors across the Los Angeles basin. Lockheed at Burbank fed the transport pipeline with twin-engine assemblies, while also planning for a heavier flow of reconnaissance frames. The region's rail yards became part of the schedule. Loads of aluminum plate extrusions and engine mounts rolled in under priority ratings, and finished wings went out on flat cars with chalked dates that matched final assembly windows, upstate or out of state. On Long Island at Bethpage, Grumman turned a cluster of compact buildings into a dense web of F-6F stations. The company had learned to treat each airplane as a kit of time-boxed tasks. Subassembly cells delivered tailplanes, control surfaces, and landing gear on tact time so that the main line never waited. Republic at Farmingdale applied similar discipline to the P-47, with its large radial engine and broad wing planform that demanded precise drill templates and repeatable rivet patterns. Out on the line, inspectors worked to a sheet that called out torque values, gauge readings, and acceptable tolerances in thousandths of an inch. The objective was not to build one great fighter. The objective was to make every third shift unit indistinguishable from every first shift unit. Detroit carried a separate burden. At Willow Run, west of Detroit, Ford erected a mile-long building and then learned how to make a moving line behave for a complex bomber. Early months were uneven. Fixtures jammed. Subassemblies arrived late. Tooling drift produced rework. Management responded by breaking the flow into smaller beats, pushing more work into feeder lines, and standardizing every motion from the way a worker picked up a pneumatic riveter to the route a forklift took between bins. The acceptance count for the B-24 rose when that choreography settled. It was a reminder that an airplane is not one thing. It is thousands of scheduled parts with metal, rubber, fabric, glass, and fasteners all due at the same minute. Engines demanded their own campaign. Pratt & Whitney ramped the R-2800 program across plants aligned to test cells that ran day and night. The Wright program for the R-600 and related types followed similar curves. Allison worked to harden the V-1710 for service conditions, and in Detroit, Packard began licensed production of the Merlin to feed lines that would accept that engine. Each block of engines moved with logs that recorded hours, temperatures, and vibration signatures from run-up. Propeller makers timed shipments so that hubs and blades met engine crates and airframe stations within the same shift. When a crate missed a window, it became visible in the Office of Statistical Control reports that compared plant schedules against actual acceptances by model. Supply lines extended beyond factory gates. The Air Service Command and the Air Transport Command plotted ferry routes that matched production calendars. From Western plants, new fighters and bombers staged through fields in Arizona, New Mexico, and Texas, then moved to East Coast embarkation points for shipment to Britain or to North Africa. In the north, the Alaska-Siberia route came online so that aircraft could be handed to Soviet crews at Ladd Field near Fairbanks and flown to Krasnoyarsk by way of stepping stones across the Yukon and Siberia. In the South Atlantic route lifted aircraft from Florida to Natal, then over water to Ascension Island and onward to West Africa. Each route had weather limits, spare parts, caches, and trained crews to turn aircraft quickly. The map was logistics turned into flight plans. Conversion work filled the spaces between these movements. Automobile plants in the Midwest stopped building cars in early 1942 and shipped machine tools, presses, and fixtures to aircraft makers according to priority codes. Tool and die shops that had cut stamping, dies for fenders and hoods learned to machine wing ribs, bulkheads, and engine mounts out of heat-treated alloy. Rubber plants changed compound recipes to suit aircraft tires and fuel hoses. Aluminum smelters set shift plans that matched rolling mill bookings for plate and sheet, and those bookings matched airframe station needs 2 or 3 months out. The War Production Board sat over these calendars like a conductor. Quality control became its own opening action. Training schools in San Diego, Los Angeles, Seattle, Wichita, Fort Worth, and Buffalo produced inspectors who could read drawings, use micrometers, and spot telltale marks of bad heat treatment or poor drill technique. Statistical sampling plans appeared on clipboards. Rework rates were tracked station by station. If a station missed its daily acceptable units, engineers walked the bay with the foreman to isolate whether the fault lay in the jig, in the work instruction, in the tooling, or in part quality. The feedback loop shortened week by week until the median unit left each station on time. Only then did acceptance figures begin to climb in a steady line that planners could trust. In parallel, Lend-Lease deliveries created additional pull on the lines. Fighter and bomber allocations were divided among domestic units training for deployment and Allied needs overseas. That division forced an honest schedule. No line could slip without consequences in 2 theaters. The reality of 2 customers sharpened management decisions about which bottleneck to open first, which subcontractor needed a second source, and which plant could absorb an extra shift. By the final quarter of 1942, the system behaved like a campaign with fronts, reserves, and timed blows. Plants launched new models only when tooling and suppliers could keep pace, and older models ran out their contracts with predictable cadence. By the start of 1943, the opening moves had achieved their purpose. Assembly lines across Seattle, Long Island, Los Angeles, Wichita, Detroit, Fort Worth, Dallas, and Buffalo were synchronized with engine plants, propeller makers, and ferry routes. The acceptance curve now reflected system behavior rather than spurts or luck. With that foundation in place, the war economy was ready to confront the next problem, set eliminating bottlenecks. Lifting monthly throughput to peak and sustaining the flow of spares and trained crews that would turn raw output into operational strength. The decisive turn came when management treated every constraint as an engineering problem with a dated fix. In early 1943, the War Production Board and the United States Army Air Forces agreed on a single rule. The system would lift throughput only where a measured bottleneck was removed and where suppliers could sustain the new rate for 3 consecutive months. That rule forced disciplined choices. Aluminum sheet moved to plants that proved they could hit takt time. Forging press minutes were reallocated to engine crankcases and propeller hubs that cleared test cells on schedule. Railcar space shifted toward subassemblies that had demonstrated low rework. The calendar became the instrument of command. Leadership decisions were specific. General Henry Arnold set a priority list by combat effect. Long-range fighters and heavy bombers moved to the top because they created air superiority and struck deep targets. Assistant Secretary Robert Lovett fixed a second rule. A plant could add a shift or open a new line only if its suppliers had signed capacity statements for castings, bearings, and instruments. Donald Nelson at the War Production Board enforced those statements with priority ratings that reached down to extrusion dies and heat treat loads. The tone of these orders was administrative, but their effect was operational. Shop floor practice changed with the same intent. Plants replaced general-purpose fixtures with dedicated jigs that constrained parts in 3 axes and reduced skill variance. Drill templates were hardened to hold hole position within thousandths of an inch over long runs. Tool rooms standardized bit geometry so that holes took the same torque and the same rivet every time. Engine builders doubled the number of endurance cells and logged each block to a common test protocol. Propeller makers posted balance readings at each station and rejected units before final assembly. The purpose of these changes was to move defects upstream and keep final lines moving at a constant beat. Quality control became quantitative. Statistical sampling plans set accept counts and reject thresholds by station and by day. Foremen carried charts that showed process capability for critical dimensions. When a dimension drifted, engineers walked the line with gauges and swapped suspect jigs before scrap rows. The Office of Statistical Control turned these local actions into national visibility. Monthly reports ranked plants by accepted units, rework hours, and missed material calls. Managers could now see which supplier threatened a schedule 2 months in the future. The next month's rail manifest changed to match. Materials policy hardened into a schedule. Bauxite shipments to smelters were dated against rolling mill bookings. Rolling mill bookings were dated against wing skin stations. Magnesium casting slots were pegged to specific engine halves and gearboxes. Rubber allocation protected tires and seals on long-lead airplanes before any new model could draw stock. Steel tube flowed to engine mount fabricators with strict lengths and wall thickness notes in the dispatch. Each decision was small. The sum produced stability at the line. A second front was manpower. Plants created structured training for line leaders and inspectors. The course length was measured in weeks. The content taught drawings, metallurgy basics, torque practice, and safe work on powered tools. Women entered these classrooms and then the bays in large numbers. Unions and companies agreed on rules that allowed 2-shift and 3-shift operations with premium pay and safety breaks. New standards cut tool change times and set floor layouts so that forklifts moved on fixed routes. The result was fewer collisions, fewer bottlenecks at parts cages, and a smoother beat on the line. Engines and fuel created their own turning points. Pratt & Whitney raised output of the R2800 by synchronizing cylinder crank and supercharger suppliers to a single takt. Wright improved flow on the R2600 and related families. Packard's licensed Merlin program matured and began to ship blocks that paired with long-range fighter airframes. Propeller plants increased pitch control actuator output so that engines could translate power into thrust efficiently through a range of altitudes. External fuel tank production expanded, including pressed paper tanks for one-time use which extended escort range without diverting scarce aluminum. Range was now a manufactured property. The calendar shows the inflection. In the second half of 1943, acceptances rose each month and held gains. Heavy bombers left Seattle, Wichita, and Omaha with fewer rework hours and higher first-pass yields. Fighters left Inglewood, Dallas, Farmingdale, and Bethpage in matched batches that could be ferried in formation. Transports and trainers sustained their own curves to support pilot pipelines and supply routes. The Allied Air Forces used this reliability to plan sustained operations. In February 1944, a coordinated series of strikes tested the new depth of spares crews and aircraft. The system held. Replacement units arrived on the dates promised. Maintenance depots had parts at hand. The enemy saw a force that could return tomorrow. Decisions about where not to spend were equally important. New models were delayed if tooling could not guarantee repeatability. Plants kept proven types in production, while teams matured the next airframe off the main line. Government-owned contractor-operated plants received new models only when their first model met stability tests for several months. The old habit of pushing premature designs into production lost to the new habit of protecting flow. Schedules produced combat power. Disruptions lost sorties in named theaters. Spare parts became an explicit product line. The United States Army Air Forces wrote contracts that priced spares separately and demanded delivery curves equal to airplane curves with a 3-month lag. Engine makers shipped pallets of magnetos, carburetors, pumps, and reduction gear parts on fixed cycles. Airframe makers boxed control surfaces, canopies, and landing gear struts with label sets that matched depot catalog systems. The Air Service Command plotted these flows onto depot maps in Britain, North Africa, India, and the Pacific. A destroyed airplane was a loss. A grounded squadron was a failure of planning. The parts program prevented the latter. Rail and ship capacity received fixes as well. The War Production Board coordinated with the Office of Defense Transportation to assign priority trains for aircraft items. Flat cars with wing racks moved on schedules that met ocean sailings. Ports created covered areas for propellers and instrument crates so that salt air did not damage finishes. Crates received larger stencil fonts and standardized item codes that matched depot manifests overseas. Each step reduced search time at the far end and sped the turn of ships and aircraft. The human factor at the top also hardened. Production councils met on fixed days with printed agenda plant-by-plant scorecards and problem lists. When a plant missed a number, the discussion asked one question: what constraint must be removed by a date on the calendar to prevent a repeat? Sometimes the answer was a new jig. Sometimes it was a second source. Sometimes it was a decision to stop introducing changes until the base process stabilized. The vocabulary of these meetings was plain. Dates, quantities, stations, people accountable. By late 1944, the results were visible in every theater. Fighter escorts ranged deeper. Heavy bombers launched at higher rates with fewer aborts. Carrier decks filled with modern fighters and torpedo airplanes because inland plants delivered on time. Training units in the interior still received enough airplanes and engines to keep pipelines full. The decisive action had not been a single raid or a sudden conversion. It had been a 2-year sequence of measured choices that turned a pledge into a system. When the system reached peak air superiority followed as a consequence rather than a surprise. The immediate results of the production surge appeared first as changes in operational calendars. In Western Europe, the 8th Air Force scheduled deep strikes in sequences that would have been impossible without reliable replacement of airplanes and engines. Fighter groups received long-range escorts on the dates promised. Heavy bomber groups launched in strength 2 days in a row, and then did it again the next week. Abort rates fell as new engines and propellers reduced failures on climb-out. Maintenance officers reported that depots issued the right spares in the right crates at the right fields. The effect was cumulative. Air superiority over Western Europe did not arrive as a single event. It arrived as a pattern that held through winter weather and through the higher loss rates that came with operations near the German frontier. At sea, the same cadence changed convoy protection. The United States Navy and the Royal Navy used carrier groups and long-range patrol aircraft to extend coverage across the mid-Atlantic gap. Production lines on Long Island and in California kept carrier decks filled with modern fighters and attack airplanes. Shipyards received aircraft that matched hangar and elevator dimensions without delays for late modifications. That detail mattered. A carrier that sailed with full complements of airframes and spare parts could keep hunter-killer groups on station longer and could return to sea sooner after brief refits. Fewer gaps in coverage meant more convoys arrived without major losses. The operational graph bent toward safety because factories treated dates as orders. On land, the benefit took a different shape. Medium bombers interdicted rail lines ahead of ground offensives. Transports and liaison aircraft multiplied the speed of staff work and the reach of artillery observation. New airplanes moved into replacement pools fast enough that armored divisions and infantry corps planners could count on consistent air support when weather allowed. The number of sorties per day rose when airfields filled with serviceable airframes and when maintenance crews had the parts to return grounded machines to flight. The production system had extended the endurance of operations. That endurance created options for commanders who now planned in weeks instead of in days. Allied cooperation absorbed a large share of the output and amplified the consequence. British training commands integrated American trainers and engines into their schools. Soviet units received fighters, bombers, and transports along routes that began at factories in the American West and crossed Alaska and Siberia. Chinese and Indian theaters accepted transports that kept air routes open over mountains and jungle. Lend-lease was more than a diplomatic phrase. It was a schedule of serial numbers and shipping manifests that arrived on time. When Soviet ground units recovered cities through 1943 and 1944, they did so with a rear area that included American trucks and American aircraft moving fuel and ammunition. When the Royal Air Force and the United States Army Air Forces alternated day and night attacks, they did so with replacement pools that could absorb losses and return to target sets without long pauses. The numbers on ledger pages were matched by human effects in the bays and on the lines. Employment climbed in the very regions where new plants had risen. Women and men who had never touched precision tools learned to drill to a template and to measure to 1,000th of an inch. Shift whistles set the rhythm of towns near Detroit, Long Island. Seattle, Los Angeles, Wichita, Dallas, and Fort Worth. Unions and management wrote rules for safety breaks and for 3-shift rotation. Pay stubs supported households and war bond drives. The social landscape changed because airplanes required hands at stations with deadlines that did not stop at sunset. The cost in materials and in attention was high, and the system paid it by choice. Automobile production halted in early 1942 so that steel, rubber, and floor space could move to flight. Consumer goods shrank to a shadow of their pre-war volume. Rail timetables were rewritten to give priority to wing racks, engine crates, and propeller boxes. Local bottlenecks still appeared. A mill might miss a heat treat window. A foundry might slip a casting delivery. A flood or a blizzard might close a line for a day. What changed after 1943 was the speed with which the system isolated the failure and moved around it. The visibility created by monthly acceptance targets and by statistical control reports meant no delay stayed hidden long enough to cripple a theater plan. By 1944, the strategic consequences were clear to opponents and to allies. German fighter units that reformed after heavy losses found fresh American groups waiting for them with equal or greater strength. Anti-aircraft batteries that fired into bomber streams on Monday faced similar streams on Wednesday and again the week after. The Luftwaffe lost trained pilots faster than it could replace them. Factories inside Germany struggled under bombing and under shortages that could not be solved by management discipline alone. The asymmetry of replacement rates translated into air superiority and then into interdiction that starved rail hubs and fuel depots. Operations on the ground felt the shortage at bridges and at sidings as trains failed to arrive. In the Pacific, the same arithmetic supported a different pattern of war. Carrier task forces relied on a steady flow of new fighters and torpedo airplanes to maintain offensive pressure across island chains. Seabees and Army engineers built new runways that filled at once with fresh airframes flown from inland plants by ferry pilots and air transport crews. Very heavy bombers drew on engine and propeller spares stockpiled at depots forward of Hawaii and then at captured fields in the Marianas. When operations demanded a higher sortie rate, the supply chain stretched but did not break. That is the point. The production peak of 1944 proved powerful not only because of its size, but because of its reliability over many months. The accounting in 1945 recorded two overlapping outcomes. Combat still required large numbers of airplanes and engines through the spring and summer. At the same time, the surrender of Germany in May and the surrender of Japan in August allowed rapid cancellation of contracts. Orders for new models ended. Plants prepared to reconvert to civilian goods. Acceptance totals fell as planned. Government-owned contractor-operated facilities wrote closeout lists that covered jigs, fixtures, and presses to be stored or sold. Workers faced layoffs or transfers as lines stopped. The transition hurt in places, but it did not erase the technical skill that the years had built. That skill would move into peacetime products in the months ahead. Casualty figures and loss tables tell a parallel story that belongs to the battlefield more than to the factory floor. Air crews paid in lives for the operational pressure that sustained daily strikes. Training accidents took a toll as thousands learned to fly and to maintain complex machines at speed. Those losses do not change the arithmetic of production, but they define the human cost that the arithmetic enabled. The system delivered the machines and the parts. People flew them and fixed them and sometimes did not return. The aftermath includes both facts. Politically, the consequences inside the United States were immediate. The federal government had proven that it could finance, build, and coordinate a national network of plants and suppliers on a tight calendar. Congress and the executive had used law to align private capability with public purpose. Governors and mayors had measured new tax bases against the demands on housing, roads, and schools. Universities and technical colleges had aligned courses with industrial needs. The war ended. The memory of how to mobilize did not. Strategically, the output settled the central question that opened this story. Could the United States convert a consumer economy into an engine of air power at a speed and on a scale that would change a war? The answer was yes, and the evidence was the calendar of acceptances, the depot shelves filled with spares, the flight lines that turned over serviceable aircraft each morning, and the operations that kept returning to target sets until defenses failed. The consequences were immediate in victory and enduring in the way planners thought about national power. Production had been a campaign. Its aftermath was the map of a world in which industrial method had become a form of strategy. Historians tend to agree on three principal conclusions about the American aircraft program of 1940 to 1945. First, scale and reliability mattered more than any single model. The United States did not merely reach a high annual total. It held steady month after month, which allowed air forces to plan sequences of operations with predictable replacement of airplanes' engines and spares. Second, the management system was itself a weapon. Priority ratings, government-owned contractor-operated plants, statistical control, and dated acceptance targets created a feedback loop that found bottlenecks early and fixed them on a calendar. Third, quantity enabled choice. With airframes, engines, and crews arriving on schedule, commanders could switch effort between Western Europe, the Mediterranean, and the Pacific without starving any one theater. Debate remains on the relative weight of strategic bombing versus other uses of air power. Some scholars argue that the destruction of petroleum transportation and fighter production in Germany during 1944 was decisive. Others emphasize that interdiction, close air support, naval air, and the collapse of the Luftwaffe pilot pipeline were the true levers. There is also discussion over counterfactual allocations, whether fewer heavy bombers and more long-range escorts earlier would have reduced losses, or whether accelerating very heavy bomber programs yielded diminishing returns until bases were available. These debates turn on operations, but all assume the production base that made such choices possible. Another contested area is attribution. Political narratives sometimes credit a single leader, a single firm, or a single factory. The record shows a distributed system. The Office of Statistical Control, the War Production Board, the Air Service Command, and dozens of prime contractors and hundreds of suppliers acted together under shared schedules. The result was not a miracle, but a method measured work standard tools and jigs trained labor and transports that carried finished units and spares forward on time. The military legacy was doctrinal. Post-war air forces treated logistics, spares, pipelines, and data reporting as integral parts of combat power. The political and economic legacy was institutional. The federal government learned how to finance and coordinate complex capital projects with private management at national scale. The social legacy was skill. Millions learned precision work that migrated into peacetime manufacturing and aviation. One-sentence conclusion and call to action. The lesson of this story is that disciplined schedules turned a continental economy into combat power. If you found this useful, consult the reading list in the description and tell us in the comments which part of the production chain you want us to unpack next.